Our next speaker is David Hinks. David is the Cone Mills Professor of Textile Chemistry at North Carolina State University, and he's going to talk about some work dealing with LC, time-of-flight mass spectrometry, and something else we haven't heard about yet. So, David?
Thanks very much, Keith. If you look at the title slide, you'll notice that Keith is a co-author on this paper, and he's really been a major driver in a significant part of our project, which you're going to hear a little bit about. Anne Fraser is a graduate student that's done a lot of work as well, and Chuan-Jen Zhu and Roberta Garcia and Dita Griffiths are in the Material Science Department, part of the Analytical Instrumentation Facility at NC State, and they've done the work on the TOF SIMS, which I'm going to tell you a little bit about. So for those of you, I think a bunch of you are probably in our workshop on Monday. I'm going to try and minimize the amount of overlap that we did through the workshop in terms of method development of LC and the time-of-flight mass spectrometry, and really expand. I decided to expand out another part of the project. There'll be something new for you guys that were in the workshop. NC State, in the College of Textiles, it's the largest college of textiles in the Western world, and we're very lucky to have huge resources. We can do what we call molecules to markets. We do dye synthesis, we do polymer synthesis, we do extrusion, we can do knitting, weaving, non-wovens on a very large scale, all within our college, and we, of course, the analytical chemistry and the engineering component to that as well. We're also very lucky to have an extremely diverse textiles library. This is an image of a book, which you can take a look at the end of this session if you're interested in, and if you're interested in it, and if you're in the workshop, you would have seen it already. It's called the Detroit book. It's a collection of automotive fabric samples, and we have these books from 1955 to the present. So these are literally thousands of samples that we are using as part of this project, which I'll tell you a bit more about later. These are all domestic automobile samples and also almost all imported cars as well. So if you happen to have a 1950s car, or you grew up in the 50s or 60s, you may, I guess the projector doesn't show these images very well, but they have some really funky colors and weave structures from the 50s and 60s, much more muted these days. The goals of our project, and Claude really set me up for this really very nicely, is really to advance the science of trace evidence. Ray Palmer gave a great talk today, the Jigsaw murder, beginning this morning, and she really showed the importance of trace evidence as it relates to fibers and color. What we're trying to do is take that to a new level and be able to identify unambiguously the dyes that are present in commercial fibers, whether they're automobile or not. We've looked at disperse and acid dyes for the time being. We're now broadening to other dye classes. Our initial focus has been on the automotive fibers and also residential carpet and automotive carpet. So our other goal is to develop a searchable database based on this methodology. We've got two approaches, and Keith really did a very nice job taking us through the liquid chromatography and time-of-flight mass spectrometry methodologies that are available to us in our college and in other research groups as well, which you're going to hear about this afternoon. What you haven't heard so much about is another approach that we are using is direct dye analysis. So our goal here is to analyze dyes within or on fibers without extracting them. So can we use mass spectrometry to identify to high accuracy dyes present in fibers, and that way perhaps even eliminate the need to sacrifice any of the fiber? It's a tall order, but it's really an exciting area. So this is our, for the first part, the extraction followed by mass spectrometry. We've got the liquid chromatograph here as our Agilent system that interfaces with quadrupole time-of-flight mass spectrometer. This is the flight tube that you heard a bit about with Claude, and then if you were in the workshop, we went through that. Keith did really very well. The issue that I want to bring across for time-of-flight mass spectrometry is the increase in precision. we really have a resolution that's really outstanding, and it allows us to get to calculated masses to the third or even fourth or fifth decimal place. And so this allows us then to predict molecular formulas with great accuracy as well. And so there's a database, a free database called ChemSpider, has over 30 million samples in this open database. And if you look for a molecular weight or a formula where we have molecular weights to 3 or 4 decimal places, then this really allows you to identify one or very few molecules that are going to hit that molecular formula. So it really increases the precision. These are the dyes. I know I'm not going to take you through all of these, but one of the things that we have expertise in is both dye stuff manufacturing and the manufacture of garments, and we have great expertise in, or great collection of fibers, as I've just mentioned, but also collaboration with retailers and dye stuff manufacturers. These are the number of samples we've got for each of these, in this case, dispersed dyes, and these are the number of different manufacturers of the same dye. Some of the structures are disclosed publicly, some of them are not. The one I'm going to focus on this afternoon is Disperse Blue 60, where we've got samples from 9 different manufacturers. So let's take a look at one of those manufacturers. I'm going to hide the names of the manufacturers because they might be a little bit sensitive to some of this data, but it still is very relevant, and we know who they are. And what's interesting is this is an LC chromatogram we're using our diode array detector that is prior to the interface with the mass spec. Looking at the 660 nanometers is the blue region for blue 60. This is the lambda max. We see 2 peaks. And so they correspond to 2 dye molecules that appear to be identical in color. They have the same absorption spectrum. By MSP, they would look the same. They would not be differentiatable. But they do have different molecular structures. And in dye synthesis, it's common for the synthetic chemist to use different raw materials. There might be mixtures by choice for different properties, or they might be not by choice, just happen to be impurities. Here we have 2 compounds that we can see here. This is a methoxy-ethoxy end group, and this is just a methoxy group. And so they separate on the chromatography column, no problem. This is an extracted ion chromatogram at 380.1241. That gives you an indication of our level of precision potentially. And here's one at 424. And so these correspond to these 2 structures. So let's look at another manufacturer of this particular dye. Disperse Blue 60, again, but a different manufacturer. These structures are different. So when you look at it, they probably look very similar. One of them actually is the same. I think it's this one as one of the others. And this one is a different one. This is an ethoxy end group. So we can differentiate these very readily. There's no problem at all. The next one, here is a dye stuff manufacturer that is a single peak. And so here we have the methoxy. And so this is technically what Disperse Blue 60 should be, is this methoxy group, I believe. So it has a mass of 424, and we can see this extracted ion content here. So you can see, depending on the manufacturer, we can identify a particular dye and depending on their method of synthesis. So here's another one. Manufacturer 5 actually has 3 peaks. These are all, again, absorb at lambda max of 660. Here, this isn't the best spectrum that we pulled, but here is a UV visible spectrum. And you can see the spectra overlay very neatly. So let's take a look at this again, this manufacturer 5. Here's the diode array at 660. And here we have our 3 peaks. So we've got the 3 structures, identical color, different molecular weights. Looking at using the TOF, we can pull up the mass spec, of course. And here you can see the parent ion, the product with hydrogen, M plus H. And we sort of blew this one up just down here, this region. You can't see the numbers very well, but I think this is 380 and 381, and we can really have very high resolution in the mass spectrum because of the time of flight. We also have the capability with this system to do MSMS. So taking one of the precursor ions of 424. We know this is our Disperse Blue 60. And then in the collision cell within the mass spectrometer, we can fragment, as you can see here, to fragment these particular ions and identify them. So this increases even more our capability to identify and potentially search on these structures once we get a searchable database. So back to our Detroit book. We've developed this out, this methodology. Everything's looking very good. All of the disperse dyes that I mentioned, I think we have done 120. We've got acid dyes as well, and we're just continuing to build that out. We took one of these fibers, a few strands of this fiber. We do about 50 micrograms at the moment, but we're working on getting down our limited detection significantly. But this is a black fiber. It happens to be from a Ford F-150 2009, so if that's your car and you happen to have black fabric, then it's going to be this kind of fabric. So we extracted the dye from this fiber and analyzed it by our method LC QTOF. Here you can see the dyed array chromatograms at 660, 540, and 410, and we can see we've got mixtures here. So this peak corresponds to our blue 60 that I showed you, and this one corresponds to dispersed yellow 42. And the one in the middle, this is at 540 with a lambda max for these peaks. We don't know what that is yet. And the reason we don't know what it is because it's not in our database. And so as we build out the database further, we fully anticipate that we're going to be able to identify these dyes because we'll have all the dispersed dyes analyzed. So as a result, we can go back just quickly to the book. The idea is that we'll be able to take any one of these thousands of samples and be able to identify which dispersed dyes are present. Okay, so the summary for this side is this involves extraction and LC mass spec. We've been able to show the capability for dispersed and acid dyes. It's not surprising. It's got great resolution. The searchable LCMS database is certainly feasible. We're doing the exact mass and MSMS differentiation is possible. And the different differentiations with different manufacturers also looks really very interesting to us, and we certainly see that as being very highly powerful capability in trace evidence. These are the books here. So ultimately, what our goal is, and we'll see how far we get, is to identify the make, model, and year of a car based on a single fiber when we extract out the dyes. So let me take you to the next stage. Can we identify the dyes within fibers without extracting the dyes? The idea is that we wouldn't have to consume significant amounts of the dyed fiber. Again, this is time of flight mass spectrometry, but it's called time of flight secondary ion mass spectrometry, or TOF SIMS. It's a little bit different methodology. It doesn't use chromatography. And in brief, when we use TOF SIMS, we bombard surfaces, it could be any surface, with high energy ions, primary ions they're called. And so in our case, we have a bismuth ion source that is pulsed on a nanosecond level onto a surface, and we can actually pinpoint the ion onto a very small area and raster over an area of the material. It penetrates about 8 to 10 angstroms, so it's really on the surface. And then we generate secondary ions based on the primary ions bombarding into the material. Those secondary ions could be dye or dye fragments, and they go up, but they get extracted into the mass spectra, the MS system, and again we have a time of flight tube which determines the masses to just a high level, as I mentioned before. Okay, so this is the raster image that we have here. We can typically will raster over a 100 micron by 100 micron region and obtain a total ion image of everything that's coming off. Now, these aren't just molecular ions. These could be elemental ions as well. So you get metals analysis. It's really very versatile. And from that, you can extract certain masses and look for those and see where they are in that region. It really has a lot of interest for us, both on looking at fiber surfaces, but also inside a fiber. So we did an initial assessment of how we had a concern over low levels of dye in the fiber, and we did a series of dyings from 0.1%, which is really low, up to a high level, which is 7% of weight of the dye in the fiber. We also analyzed commercial dye powder, the surface of the dyed fabric, we analyzed by TOF SIMS, and then also cross-sections of the dyed fabric. So you can see the loadings here. Let's take a look at the dye powder first. This is basically the powder that's set into a pellet, and that's our surface. We're able to identify, here's our friend Blue 60 again, so rather than confuse you with different structures, going through the same structure. Molecular weight, as you can see, this is the methoxy-ethoxy structure, and you can see the fragment ions in the mass spectrum, no problem. We can do positive or negative. So taking the negative ion approach, we looked at a fiber surface with various dye loadings that I just showed you. And so here are the mass spectra, and you can't really see a lot of detail. We zoomed this up, just for these 4 at the bottom at the low concentration levels, we can see the ions, and these actually go out to 3-4 decimal places here of the dye at 379. That's a characteristic peak, and dye at the 423, which is the parent in negative ion mode. And so we can really go down to, our limit is about 0.1% before we get into the background noise. So it really looks very interesting for us. So that's the surface of the fiber without doing anything. But what if the surface is highly contaminated? That might be a problem for us. So we're interested also in getting onto the inside of the fiber through cross-sectioning. We have a cryomicrotome that we purchased through this project, and we can therefore cross-section at low temperature, have very little smearing of the resin or other surface contaminants, so we're relatively confident we're not getting contamination. And this is a total ion image, and then this shows you an ion master charge at 121, which is characteristic of one of the characteristic peaks of PET, and we can see the fiber content there. So what else can we do? So here's the PET as I just showed you. Here we can also look for the resin that's set in, the fiber set in. This is at 98. And then also overlay the images of the PET we put in green here, and the resin is in red. And so you can see this set in the whole image. This is, again, could be up to 100 micron square. Okay, so I'm afraid you can't see the images quite as well as you could if you were up close on a monitor. So here's the resin again, and here's the dye. You really can't see this, can you? This is unfortunate. The dye and the resin, you can see if you're actually up with the monitor, you'll be able to see this. There are blue dots in the center here where the fibers reside, and so we're really able to analyze the dye, be able to see the dye being ionized off the surface of the cross-section. Yeah, dreadful. A dreadful projector. It's unfortunate. So I'm afraid you can't see it, but this is at a 7% loading going down to a low concentration. So this is just for visual effect. But the next question you should be asking is, okay, so you can see the dye in the fiber. We've got different dye concentrations. Can we actually correlate the amount of dye in the fiber to these mass intensities? And the answer is yes, we can. So here's the correlation of percent dye in the fiber versus the mass intensities. And what we did was we took the ion of interest, in this case is 379, corresponding to this higher linear curve here, and we normalized it with 350 to 357, which is an ion present in the polyester. So that gives us a normalizing against the ion intensity. Oops. And then we did it for another ion, 423, which is our parent ion. So you can see a really nice linear correlation with the dye loading versus the mass intensity. We did that also for the dye in the cross-section. So we can do it on the surface of the fiber and also the cross-section. Really quite an interesting approach. We haven't extracted the dye, remember, and so we're building this out to see what the scope and limitations of this approach is. So the summary for TOF SIMS is we can analyze dye powders, we can analyze dye on the fiber surface and in cross-section, and we can get a linear correlation between dye concentration and the mass intensities. The other benefit of cross-section is via cryomicrotomy. We think we can avoid potentially surface-contaminated material, don't have to necessarily clean the material, if it's degraded on the surface. So I'd like to just, in closing, acknowledge the National Institute of Justice that's been supported this project. You can see the award there, and I really thank you for your time.